check. Somebody checks the YouTube. Hello. Yeah. How are you? Fine. Do you speak French? Yeah. Can you check the Can you hear me? It's fine. It's okay. No, checking the YouTube for the streaming. Yeah. Okay. It's fine. Yes. Yeah. 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 We have. Yes, we have the John has access to the Zoom. He's the host of the Zoom meeting, so he can. Yeah, I can stop it. I can. Yeah, I can stop. Yes. Yeah. Means that you have a little bit. I can feel it. Will you see the link? No, I mean, I can create another Zoom. Yeah. Or you can send me the same way, but we can ask it not really. I mean, if you stop the broadcast, yeah, then we can remove the component. Yeah. This is what we have to do anyway. Yeah, it's fine. Yeah. Your conference like you have a screen like no, there is no screen. Here or if they join, then I can see how it works because for now nobody joined, so I don't know. No. Because they don't have the second screen here, so don't know. They have a microphone, but I think I don't need it. But maybe it's useful for the question.
Probably it's better to let them question first.
Yeah.
So they can maybe, well, I guess that display will be recorded.
Yeah.
The Tom is.
Yeah.
You're missing a
This one, yes, yes, this one is missing. It's because it's the old version. Yeah, I'm checking. No, not yet. So there will be 3 online. Yeah, because
Hello, hello Arnab.
hello.
Do you hear me?
Yes, we can hear you.
If yes, I cannot hear you.
You can. You
Ah,
can. Okay. Is it fine?
it's fine for me. Hello, nice to meet you.
Nice to meet you too.
Sorry, it was not possible for me to be with you because I have some
Yeah.
trouble with the train this morning.
Yes, understand.
Sorry.
Yeah, we are just waiting for 2 other jury members. They are online, so we are
O-
just waiting for them to start.
Okay, no problem. Arnab,
Yes.
I don't know if your jury member is speaking because I'm not able to hear.
Yes, no, nobody's speaking at the moment.
Okay.
Yeah, it's just, yeah. Hello. So everybody is here, I guess. Yeah. So we can start. Oh, all of you can hear me? Okay, yes.
Yes.
Yeah, so if you want to use the microphone, it's fine. So, yeah, I can give it. Yes, I can show. Yeah, just. Maybe. You have to turn it on. Yeah. Just a sec. Okay. Okay.
Can you hear us? Cédric?
You have to maybe louder.
So this doesn't work for them.
No.
Okay.
Because it doesn't connect with the,
I have a question.
yeah.
Then we have to go there. We have to connect here with computer to
Yeah, that's also possible.
the yeah. It's all- what that starts.
Oh, okay.
Hello, Franck. Bonjour, Franck. It's really difficult to hear you. Salut.
Yes, with my microphone, you hear me?
It will be noise.
Oh. I think this for the question, right? Okay, biomechanics. So I'm gonna say a few words about the jury. We have two reviewers for the work. One is online, Cédric DEMONCEAUX. I'm not sure if you can hear me well. So Cédric is professor at University of Bourgogne and with ICB lab. And we have another reviewer here in the room, Franck DAVOINE. He's a senior researcher with INSA Lyon and heads with the Lyon lab. And in the jury, we have also online DRUMMOND, who is a professor with his Melbourne Connect Chair of Digital Innovation for Society in the School of Computing and Information Systems at the University of Melbourne. We have online also Professor Srinath, who is an assistant professor at Brown University in the United States, and he's the leader of IVL, Interactive 3D Vision and Learning Lab. So here in the room, we also have Professor Tarek, HAMEL. He's a professor at Université Côte. He's the co-director of PhD work. And COMPORT, who is a researcher with CNRS, the thesis director. And I'm Jean-Martin, a professor at Université Côte. So you have 45 minutes to do the work. May I ask if you can switch your PowerPoint from PowerPoint to Thank you.
Okay. Can you hear me fine now? Is everybody online?
Yes, but could you share your screen?
Oh, yes. Sorry. Yes. Okay. Now you should be able to see my screen.
That's perfect.
Okay. So, hello everyone. Thank you for joining for my PhD thesis defense. My name is Arnab Dey, and today I will be presenting my PhD thesis on neural rendering for 3D human representation with biomechanics features. This work was conducted at Laboratory I3S, CNRS at University Côte in collaboration with Brown University. Here is an example of 3D human reconstruction. So what is 3D human reconstruction? 3D human reconstruction is the process of creating detailed 3D human model, bodies, and faces. It involves achieving high visual quality, accurate geometry, and detailed underlying structure, while also representing the physical properties and natural forces acting on the human body. 3D human reconstruction can be categorized in 4 different aspects. So we have, based on the input views, representation type, object representation, and type of supervision. For input views, we have single views, multiple views. For representation, it can be based on the point cloud, mesh, voxels, based explicit representation, or implicit representation like neural radiance field, which we will discuss today later. So in case of the object representation, it can be just for single human or multiple humans or scene representation, whole scene representation. For type of supervision, it can be images, RGBD, and or parametric models, along with other kind of data. So in recent years, 3D human reconstruction gained a significant popularity because of its application in various domains, such as entertainment. For entertainment, AR, VR, movies, video games, having a custom 3D human avatar is a significant improvement for user interactions and user engagement. For medical domain, having a accurate, detailed 3D human reconstruction can be helpful for diagnosis, patient monitoring, and rehabilitation. For robotics, human-computer interaction and navigation. For last but not least, for sports performance analysis, performance improvement, and feedback, having 3D human reconstruction can be very helpful. Objective for this PhD thesis is to develop a deep learning approach which takes sparse multi-view images like this and output 3D human reconstruction with biomechanics features such as 2D key point, dense pose, along with geometry in real time. We can divide this goal of this thesis in 3 key objectives. So first, developing a photorealistic 3D human avatar. Second, integrating biomechanics feature into this avatar. And third, achieve real-time performance. Their corresponding research questions are as follows. First, how can we create photorealistic 3D human avatar using deep learning? Second, how can we integrate biomechanical features into these avatars? And third, and finally, can this be done in real time? This presentation is divided into 3 parts, each parts corresponding to each contribution to address the previously mentioned research questions. So first, depth-guided neural radiance field. Second, NERF with biomechanics features. And last, real-time 3D human reconstruction with biomechanics features. Before dive deep into each of these contributions, I will present a short introduction of neural radiance field or NERF. So NERF is a scene representation technique where a neural network is used to parameterize the scene, neural radiance field, and density. NERF takes multi-view images as an input and optimize the neural network using these images as shown here. So starts with different multiple images of the scene and then optimize. And finally, it can generate, after optimization, the trained model can generate novel views from different angles. If we take a deep dive into the process of the training neural radiance field, first, given an input image, we generate rays. Rays are starting from the camera origin, passes through the pixels towards the scene. And then we sample points, 3D points along these rays like this. And these 3D sample points are used as an input to the MLP. And we have the location of the 3D point and viewing direction. And output is their corresponding radiance and volume density, as shown here. And as you can also see in the video, it's clearly explained how this process is done. The whole method is end-to-end differentiable and optimized using the photometric loss by comparing the ground truth and predicted pixel color, like as shown in this formula. The predicted pixel color are generated using a technique called volume rendering, where predicted radiance and volume density, as we have seen in the previous slide, is of each of these 3D points along the ray is blended together using this volume rendering, as shown here in this formula in the bottom. So the NERF, the trained NERF model can generate amazing photorealistic novel views like this. And these novel views are, they represent the details of the scenes in very intricate details with lightings and everything. Another relevant technique for this thesis is MIP-NERF, which addresses some of the drawbacks of neural radiance field, the vanilla NERF method. The MIP-NERF uses conical frustum instead of samples along the viewing ray to address the aliasing artifacts and multi-resolution training data. So in case of the NERF, we use single ray and sample points along the ray. In case of the MIP-NERF, we uses a cone, and this part of this cone called conical frustrums. In case of the MIP-NERF, the cones are generated from the camera center, similar to the NERF, and passes through the pixel. Instead of sampling point, MIP-NERF uses integrated positional encoding to encode 3D Gaussian approximation of these conical frustrums. The early neural radiance field-based methods became significantly popular for their benefits, such as compact scene representation, continuous scene representation, simplicity of the whole methods, and domain agonistic. Also, these early NERF-based methods also had some significant drawbacks in terms of slow training and rendering time. They are only limited to static scenes, and the representation is inflexible for editing or manipulation. And they also need a large amount of calibrated input images. These drawbacks open up new field of research and new possibilities for future work. To address some of these limitations of early NERF methods, we proposed depth-guided neural radiance field, which lead us to the first contribution of this PhD thesis, depth-guided NERF. Here, the key idea here is to use additional information such as depth maps, as seen here, to improve the quality of NERF reconstruction, at the same time reduce training time. In this part, we propose a novel approach for incorporating depth informations with neural radiance field. Proposed an efficient depth-guided local sampling strategy for faster training, and proposed a combined loss function for photometric and geometric supervision, and also proposed an adaptive local sampling strategy to handle depth uncertainty. The overview of the proposed method is presented here. The input to the neural network is integrated positional encoding, similar to MIP-NERF, and outputs are radiance, corresponding radiance, and volume density, similar to NERF and MIP-NERF. And then finally, we use volume rendering to render final pixel color and depth maps. The proposed method uses cones similar to MIP-NERF, and the conical frustrums are approximated as 3D Gaussians with mean and covariance. And then integrated positional encoding of these conical frustrums can be represented using this formula, and these integrated positional encodings are used as an input to the MLP. The proposed method uses single multilayer perceptron compared to the original NERF method, which uses 2 multilayer perceptron and much larger network, which decreases the training and inference time in our case. The MLP has, in our case, the MLP has 5 layers with ReLU activation functions and last layer with sigmoid activation. The color and the depth is predicted using the volume rendering, similar to the original NERF methods. Depth can be estimated with similar formula as the color, as shown here. The proposed method is end-to-end differentiable and optimized using the photometric and geometric loss together. The depth loss is a L1 distance between the predicted and ground truth depth, and it's normalized by the variance of the depth to discourage the weights with high uncertainty. One of the key contribution of this proposed method is proposed local sampling strategy, which uses depth information to intelligently sample close to the surface and avoid empty spaces. Local sampling reduces number of samples needed per ray. As a result, it reduced training and inference time. 3 different sampling strategies were proposed, namely stratified, Gaussian, and adaptive sampling. In case of the adaptive sampling, the Gaussian distribution with varying standard deviation is used, and it is calculated using the formula here. The standard deviation decreases with number of epochs to mimic course to find training, and also take into account the depth uncertainty, which is increases with distance from camera center. For the experiment, we designed a unique simulated dataset with 4 different scenes, as shown here: Lego scene, cube, human, and drums. Each of the scene has their importance. Like the Lego is very common for neural rendering. In the drums, there is intricate details and intricate geometry, and the human is, for our thesis purposes, is an important topic. And so each of this scene data set has 3 different training set, test set, and validation set. Also has 3 different variants depending on the number of inputs images. And let's look at the photometric and geometric result of this proposed method. We tested our method on our dataset, and here we presented the qualitative and quantitative results. So here we have the predicted RGB images compared to the ground truth RGB images, and the predicted depth, and we have the depth error. In this slide, we provide 3 different results. First, this table compares 3 different proposed sampling strategies and show the adaptive sampling performs significantly better than the others. As you can see in the table 1, we have the adaptive sampling perform the best and achieve best novel view synthesis, and also achieve this very close to the depth estimation compared to the other method. In second, we show that the proposed method perform well even when very limited number of images are available. So in the second table, we show that when there is different number of input images are present, the novel view synthesis quality also increases with increasing number of views. But in our case, even with very less number of input images, our method performs significantly well compared to the other, and also takes significantly less time to train. And third, we show that the relationship between the number of samples, novel view quality, and training time. It shows that the proposed method perform very well, even with a fraction of samples. So we show that even with 16 samples, our proposed method perform very close to when there is even 128 samples. It's because of our local sampling strategy. Here we present the comparison between the proposed method and other state-of-the-art method. The proposed method provide a better geometric estimations and faster training. As you can see in the table, we have the DRUMMOND achieve the best novel view synthesis, but to note that the DRUMMOND only limited to forward-facing scenes, and they takes also 5 times more time to train than our method. We have also tested our proposed methods on more challenging real-world dataset, and where we tested our methods with 3 different datasets where the depth maps are very has noise present, and we can see still our method is working. We have also performed additional experiment with noisy depth data and compare with DRUMMOND, which also uses the depth information as an input. For these experiments, we added noise with the depth map to replicate uncertainty inherent in the depth measurement. The proposed method performs significantly better compared to the DRUMMOND in novel view synthesis and depth estimation. you can see in the qualitative results, our methods estimate all the intricate details compared to the DUNERF, which loses many of the geometric details. The experiment shows the proposed method capable of achieving great novel view synthesis even with a few input images as low as 8. Also, the proposed method is a significant faster to train compared to the other state-of-the-art methods, and it can be 3 to 5 times faster than other methods. And finally, the proposed method produce better geometric quality compared to other method because of the depth supervision. To conclude, the proposed method MIPNERV RGBT proposes a novel architecture to integrate depth informations with neural radiance field. Propose a novel depth-guided sampling strategy with result in 3 to 5 times faster training. And the proposed method also achieve overall better photometric and geometric quality compared to the other state-of-the-art method. This work has been published in WSCG 2022 and Eurographics 2022. Second contribution of this PhD thesis about NERF with biomechanics feature. The second contribution of the PhD thesis is the NERF with biomechanics feature. As we discussed, the proposed method takes sparse multi-view images as an input to the network, as shown here. And the output is the corresponding novel views and human features, such as dense pose or 2D key points. In this part, we proposed a novel human NERF method capable of estimating biomechanics features such as 2D and 3D key points. We proposed a novel geometric generalizable NERF architecture capable of estimating integrated human features. The proposed method also capable of estimating more complex features such as dense pose. The proposed method is capable of rendering at an interactive frame rate. Overview of the proposed method is presented here, and the proposed method also known as GH-NERF in short. So in the proposed method, it takes multi-view images as an input and output the novel views and its corresponding human features. The normal NERF method takes input 3D query points and viewing direction, as we have shown before, and output radiance and volume density. Can be represented using this formula here. But in case of the generalizable NERF model are conditioned on input images. The encoded image features are used as an input to the network corresponding to the query points to condition the NERF model on input images. Where, as you can see in this formula, we have pi of x, which is the projection functions to project the 3D point x back to the image coordinate and to extract the pixel aligned image feature corresponding to the 3D points. The proposed GH-NERF uses two image encoder, one for multi-scale feature encoding and another for human feature encoding. We experimented two different kind of human feature encoder, more classical RASNet and Vision transformer-based Dino feature, as you can see. And for the multi-scale image encoder, we used a CNN-based encoder to encode image features in 3 different scales, as shown here. GH-NERF uses depth-guided sampling to improve efficiency. First, multi-scale image features are used to create the cascaded cost volume and pass through a 3D CNN to generate depth probability volume, which is then used to generate a depth probability for each pixel, as shown here. Yeah, and also this 3D feature volume from the 3D CNN also used to generate a voxel aligned feature here. For each query point X corresponding to the corresponding image and voxel features are combined and used as an input to the NERF MLP. The NERF MLP output an intermediate NERF feature. So we take the input image features and voxel feature pass through the MLP here and get our intermediate nerve feature. Then we use intermediate nerve features are combined with the human feature encoding before inputting to a small MLP head, which outputs the human feature. As you can see, we have the intermediate feature concatenated with human feature passed through a smaller MLP. The final human feature can be generated using the volume rendering similar to color to estimate 3D consistent human feature. In our case, we render heat maps corresponding to each joint as human feature. The output of the volume rendering is a heat map corresponding to each joint as shown here in this image. And in total, we have 25 joints and each joint correspond to a single heat map. So we have 25 heat maps here. To generate the final 2D joint location, first Gaussian filter is applied to each of the heat map. Then binary connected region is generated using thresholding. Then finally, the pixel corresponding to the 2D joint is decided by pixel locations with the peak heat map value within that binary map. The whole method is end-to-end differentiable and can be optimized together using a combined loss function as shown here. Where color and the heat map loss is a L2 distance between the predicted and estimated color and depth. Color and the heat maps. Apart from that, we also employ a perceptual loss to compare the image patches. Similarly here as. To test our method, we have used two different kind of dataset. ZoomOCAP, it's a real world dataset, and Render People, it's a synthetic human dataset. For ZoomOCAP, we have 9 dynamic sequences of real world scene, and each has multi-view images, mask, camera parameter, 2D joints, and 3D joint location. And for Render People, it has 500 dynamic simulated scenes. Each has also multi-view images, mask, camera parameter, and 2D joint as ground truth. Here we present the novel view synthesis result of the proposed GH-NERV method. The table shows the proposed method achieve best result compared to the other state-of-the-art method, which can be seen in this figure. As you can see in this table, our proposed method achieved best PSNR compared to the other state-of-the-art method, and while also predicting additional feature compared to the other state-of-the-art method. And in the image, you can see our proposed method capture more details in the novel views. The novel view synthesis and key point estimation in interactive frame rate is shown here. As you can see, the estimated 2D key points are marked with these red dots in the image, and this is an interactive frame rate estimated by the our proposed method. Here, here we show that the comparison between two types of human feature encoder in two different datasets. From the table, we can conclude that the dyno-based encoder perform better for the 2D pose estimation task as shown here. And we also compare visually the proposed two different kind of encoder and their estimated 2D key points. As you can see, dyno perform better visually. We compare the proposed method with other state-of-the-art 2D pose estimation algorithms, such as OpenPose and AlphaPose. The proposed method perform better compared to the other OpenPose and AlphaPose in 2D pose estimation tasks, as shown in the table 1. The table 2, in the table 2, we have shown that the proposed method is not limited to key point estimation. It can be used to estimate more complex human feature such as dense pose by modifying the network a little bit with last few layers. The qualitative results can be seen here, as we shown here our estimated dense pose and the absolute error compared to the ground truth. We have compared the proposed method in real-time performance with other state-of-the-art method in table 3. The proposed method achieved near real-time performance while estimating additional human features like 2D pose. As we can see, even though eNerve achieved better FPS, but we estimate more human features. It's eNerve only estimate novel views. We design an interactive software for free viewpoint novel view synthesis. So in this software, you can use your mouse to wander around and also change the parameter of the camera angles and etc. To sum up all the experiment, we achieved better novel view synthesis compared to the other state-of-the-art method. We achieved best 2D pose estimation compared to the other state-of-the-art 2D pose estimation models. We compared two different human feature encoding for this task of 2D key point estimation. In summary, we introduced a novel architecture that and first of its kind to estimate human avatar with biomechanics features using NERF. Compared different types of human feature encoder for 2D pose estimation task, and shown that the proposed method can be extended to other generalizable human features like dense pose. Also, we show that we managed to achieve all this in near real-time performance. These findings have been published in CBPR workshop and IEEE CHI conference in 2024. Next part of this presentation will be focusing on the Gaussian splatting techniques. So first, I will give a short overview of Gaussian splatting. The Gaussian splatting was introduced in 2023 as an alternative to neural radiance field. Gaussian splatting combined best of the both worlds by combining the implicit and explicit representation. It uses a set of 3D Gaussian to represent the scene and volume rendering for novel view synthesis. In Gaussian splatting, a scene is represented using a set of 3D Gaussian where each Gaussian has some optimizable parameters. As you can see, this scene is represented using the 3D Gaussians, and if we look into a small part, we can see each Gaussian representing some part of the scene. Each 3D Gaussian can be represented by its mean and covariance as shown in this formula. And the 3D covariance can be broken down into rotation and scaling matrices. Generally, the Gaussians are initialized using a sparse point cloud generated by structure from motion algorithm. Next, 3D Gaussians are projected into 2D image plane, also known as splatting technique. 2D covariance of the Gaussians can be calculated using the viewing transformation matrix W and Jacobian of the affine approximation of the projective transform J, as shown in this formula. During the optimization process, new Gaussians are created and some Gaussians are removed, also known as the adaptive control. If a Gaussian has opacity less than the threshold, they are removed. If in the under reconstructed area like this, Gaussians are cloned and added, and in over reconstructed area, Gaussians are split into smaller Gaussian to better represent this geometry. The whole method is end-to-end differentiable and optimized using a photometric loss between the ground truth and predicted image. The 2D Gaussians are rasterized using rasterize, and to speed up the rasterization process, they use patch-based rasterizer and also pre-sort the Gaussians based on their depth. The Gaussian splatting method achieve impressive results and great real-time rendering speed. And we can see some of the results of the Gaussian splatting method. The last part of this presentation will focus on learning 3D human avatar with biomechanics feature in real time. Our third contribution for this thesis is real-time 3D human reconstruction with biomechanics feature, which aims to address the final research question to estimate 3D human avatar with features in real time. The proposed method HF Gaussians takes multi-view images and then output they are called novel views, corresponding human features, and 3D pose at almost 26 FPS. In this work, we proposed a generalizable Gaussian splatting with biomechanics feature capable of estimating 2D and 3D pose along with dense pose. We also proposed a novel 3D pose regression network, which takes point cloud as an input and estimates 3D pose in real time. Also, we proposed a novel feature splatting for human feature estimation using the Gaussian splatting. And finally, we also show that this method is capable of real-time 3D human estimations with features. The overview of the proposed method can be seen here, and given a target view, the input to the method is a two neighboring source views. Output is the network is 3D pose, novel view, and corresponding human feature. First part of the method is depth estimator, a module which estimates the depth maps corresponding to each of the source views as this module. So first multi-scale image features are generated using an image encoder from the source views, and then it estimates the multi-scale image maps, and which is then used for generating a cascaded cost volume and iteratively used for generating the final depth maps. Using also for the depth map also uses the camera parameter. Another important part of the network is the pose regression network, which takes estimated depth maps as an input and convert to the point cloud using the corresponding camera parameter and subject mask. As both point clouds are in the same world frame, they are combined and sampled for 2048 points in random as an input to the pose regression network. We have used three different point cloud classification background, namely PointNet, DGC, and point transform. The previously mentioned background architectures were not suitable for real-time 3D pose estimations in our case. For that reason, we developed a new pose regression network, which combines the local features from DGCNN-based encoder and global features from PointNet-based encoder, and decode using the 3 layers multi-layer perceptron and outputting 3D pose as shown here. Yeah. So, third part of the network is Gaussian parameter estimation module, where the depth encodings are generated using a depth encoder and combined with the multi-scale image features here, and use a 2D CNN 2D unit architecture to decode and finally pass through different heads of 2D CNN-based architecture to get our final feature maps corresponding to each of the parameters of Gaussian. These prediction sets are based on 2D convolution layer to estimate Gaussian parameter maps. Finally, 3D Gaussians are estimated parameters are rasterized to generate final color image and pixel-wise human feature, calculated similar to the color image shown here. Then the smaller MLP-based decoder network is used to decode the human feature to final dense pose, as shown here. The use of the feature splatting technique for dense pose estimations is important because we show here that the performance of our method without the feature splatting and with feature splatting. Without the feature splatting, the Gaussian struggles to represent both RGB values and feature attributes simultaneously, but using the feature splatting effectively separate the RGB values with feature attributes. And the MLP-based decoder in the end learns to predict the final dense pose from the splatted features. The proposed method is trained in 2 stages. First, in stage 1, we only use the depth estimation module to train for 40,000 iteration and optimize using the depth loss, as shown here. But in the second stage, we train the whole model together with a combined loss function which include the photometric loss, depth loss, pose loss, and the feature loss. In case of the pose loss, it's just L2 distance between the predicted and ground truth 3D pose, and for the feature loss is a L1 distance between the ground truth and the predicted human feature. For the training, we have generated new dataset based on the T-Human 2.0, and we have compared this dataset with other dataset available. And we started with 526 different scans of human, and then generated 512 by 512 images, corresponding ground truth dense pose, 3D key points, 2D key points, and subject mass. For testing, we use two different datasets, T-Human 2.0 real-world dataset and T-Human 4.0 real-world dataset for our experiments. Here we present the novel view synthesis result for proposed method and compare with other state-of-the-art method for similar tasks. As you can see, our proposed method performs very well compared to the other state-of-the-art method, even though inner GPS cautions can only predict novel view synthesis. In our case, we predict also additional human features. And for the GH-NERF, it also estimates the dense pose and 2D pose, but it cannot estimate dense pose and 2D pose at the same simultaneously in real time. Some more results can be seen here as we presented some novel view synthesis, dense pose, and 3D pose. We have also applied our trained model on previously unseen real-world dataset without any fine-tuning and represented the real-time performance here. So we have the novel view synthesis, dense pose, and 3D pose. One thing to note is we applied our trained model directly on this unseen data without any fine-tuning. We have also tested our model on T-Human 4.0 dataset and compared with other state-of-the-art method and proposed the method achieve best quality for novel view synthesis. As you can see, our proposed method even keeps a lot of the details in the images compared to the other method. We have also compared our proposed method, proposed pose regression network with other three common point cloud classification background, as we previously mentioned, like a PointNet, DGCNN, and point transformer. As you can see, our proposed method performs significantly better compared to the other backbones in case of the 3D pose estimation. This plot shows that the 3D pose estimation performance versus inference time. The proposed network shows it achieved better performance compared to the other method while being as fast as some smaller fast backbone like PointNet. Here we compare the qualitative results of each of these 3D pose regression networks, and we show that the predicted 3D pose by PointNet, DGCN, and point transformer at our proposed network. We have estimated also 2D pose using the pose regression network we have shown before. We just modified the last few layers of the network to estimate 2D pose instead of 3D pose. Here we compare our 2D pose estimation results with GH-NERF, which was our previous method, and we show that our method performed well compared to the GH-NERF. Here as visually also. Our method is also capable of estimating dense pose. So we compare our method with GH-NERF, which also capable of estimating dense pose. And as you can see from the images, our method perform better in the dense pose estimation. We achieve almost like 25 FPS in real-time performance, and we compare this with other state-of-the-art method, and we also compare different 3D pose regression network. To summarize, we introduced a generalizable human Gaussian splatting method for 3D human representation with integrated biomechanics feature. We proposed an efficient 3D pose regression model for 3D pose estimation. We proposed the method capable of estimating photometric, geometric, 2D, 3D pose and dense pose simultaneously in real time and compared different kind of pose estimation model. This work also been submitted to WSCV and currently under the review. If we look back at the research questions we have proposed in the beginning of this presentation, to address first research question, we introduced a novel approach called MIPNERV RGBD to show that the neural rendering can be used to generate photorealistic 3D reconstruction, including human subject. Then we proposed GHNERV to show that how to estimate biomechanics features with neural radiance field. And finally, we show that the Gaussian splatting can be used to estimate 3D human with biomechanics features in real time, which achieve the final goal of this thesis. Even though we have made significant progress in 3D human reconstruction in this thesis, there is still plenty of challenges remain and with the possibility of future works. So current research only focuses on single humans, and it can be extended to multiple human scenes, and it can be also broaden the applications of this kind of techniques. Currently, the method is generalizable to human subjects only, but it can be extended to in future for the other articulated objects or animals. Current method is efficient for real-time rendering, but it's still not efficient for the training time, and it still takes a significant amount of time to train, so it can be improved in future work. And finally, the current model does not take into account the temporal information present in the dynamic scenes, which can be improved in future research to take into account the dynamic informations present in the dynamic scene. In this slide, I have listed all the publication we have published during the PhD and also in the process of publication. Finally, before I finish this presentation, I would like to thank all the jury members for taking the time to review my thesis and be here today. Thank you, everyone, for being here. If you have any question, please let me know.
Okay, thanks, Arnab.
Yeah.
For the next speech. If the remote members of the jury are still here, I would like to ask Cédric DEMONCEAUX to start with the questions. I remind that Cédric is full professor at Université de Bourgogne. Can you hear us, Cédric?
Hello, I heard that it's my turn. I'm not sure because I cannot hear you correctly. Is it my?
Yes.
Okay, sorry.
Yeah,
okay.
yeah.
First of all, I would like to thank your supervisor, Arnab, for this invitation. Unfortunately, it was not possible for me to be with you because I have some trouble with my train this morning. So I'm so sorry for that. Thanks for your presentation. It's a really dynamic presentation. You had some video. It's really interesting to watch this video for explaining what you did. It's really interesting. So congrats for that. Your presentation was really dynamic and really easy to follow. So you explain every part of your work, your 3 contribution, which is really important and interesting. So congrats for that.
Thank you.
In terms of contribution, you work with really important topic in computer vision right now. Really difficult to find some contribution in this topic because there are a lot of methods using NERF approaches and also Gaussian splatting approaches, as you mentioned during your manuscript, and during your presentation. So it was, I think, difficult for you to find contribution in this way, but you did it. Congrats for that.
Thank you.
I've got a couple of questions about your work. Maybe about the first contribution that you take into account the depth information in the nerve formalism. Just in general way, I'm wondering if you can generalize your problem if you use another kind of sensors. You suppose that you have an RGBD sensor, so you have color and depth information for every pixel of your image of your cameras. But sometimes we use other sensors like LiDAR and camera, for instance, when you deal with automatic vehicle and so on. And so you have for every picture you have color information, but you have a sparse not dense, but sparse information in terms of depth. So could you, in your opinion, could you extend your modelization by taking into account that some you don't know the depth of some pixel?
Yeah, so like I think there has been previously some research paper use this kind of techniques, like which uses either the sparse depth from the structure from motion algorithm or even LiDAR. In this case, like what generally is used is that you use the sparse depth map to estimate a dense depth map, and then use the dense depth map for this for the 3D reconstruction or input as a neural radiance field. So one of the way is to get the sparse depth map or the depth points from the LiDAR or structure from motion, and then use another network. Like I think Nerfing MBS is using similar techniques to generate a dense depth map from the sparse depths, and then use that for rendering and making it efficient, or what we want to do. Is it clear?
Yeah, yes. Is it? Yeah, I think it could be a good way. Wait, yes. So finally, you modify your MIP nerve by taking into account the depth, the distance of the pixel of the physical point. Thanks to that, you obtain a smaller MLP, and you did a kind of a local sampling. And about the comparison with the others method, I didn't see in your manuscript and in your slide maybe 29. Yes, 29.
With 29.
29.
Okay.
So this is, yeah, for instance, this is your results on real data, but you don't see any comparison with the other method.
Yeah, because yes, so we tried our method on real world dataset after we published, I think, just to like validate our method if it works on the real data or not, because and also we didn't compare with other method in real world, because this real dataset also had a lot of problems with the depth maps. So a lot of the methods which uses the depth maps, like DoNerf and everything else, DoNerf is only forward facing. So this kind of data cannot be used. And so in the end, we didn't really have opportunity to do compare with other method.
Okay, I see. So in your contribution, you do a local sampling for the depth. So
yes.
The classical one, or using adaptive Gaussian. So finally, you keep the adaptive Gaussian.
Yes.
Okay.
So we compare all three of them. So basically, in case of the local sampling, we started with 3 different techniques, like stratified, Gaussian, and adaptive. And then we saw adaptive was performing better, because in our case, we didn't have 2 networks. Like in case of the nerve, they have fine and coarse network to put the sample very close to the surface. But as in our case, we didn't have 2 different networks. We had just the one network. So adaptive sampling kind of assume this course to find training while doing different epochs, and as it goes to it's trained for more epochs. Yeah, so adaptive sampling was performing better.
So in this contribution, you did a strong hypothesis that you suppose that you know the depths, but for sure, specifically with RGBD sensors, the depth is noisy. So this is why you introduce some noise sometimes in a, I don't know when exactly, but you compare,
This one.
This is one. So you had only Gaussian noise on depths. So with a standard deviation 0.001, is it enough, or did you try with other Gaussian noise? And what is also the behavior of your method? I mean, local sampling according to this noisy depth.
Yeah. So as you said, we use the Gaussian noise, but this noise is added in the inverse depth. So it kind of increases with as we go far from the camera, basically with increasing depth. Yes, we tried few different Gaussian noise. Obviously, if we add more noise, it was complicated, especially for the background. It was network was not able to optimize properly, but we find there is a limit of like how much noise we can add, and in that limit the method works.
Okay, but what is the behavior of your method according to the local sampling with noise?
Yes, so if the noise is small, like 0.01 or something, our adaptive sampling can work still, because we start with the kind of a bigger bound around the noise, which if we think that there is the actual depth is some point, and then we add this noise on the depth. So in case of the adaptive sampling, it starts with a bigger Gaussian, and then it's converged slowly as the optimization goes on. So if the noise is small, the method can still optimize, and find the true depth.
Okay, I see. So this method is really interesting because this method is generic, whatever the object you have to reconstruct. About the other contribution, so you suppose that you have to construct a human people. And you mentioned that your method does not work on other objects. So what is the problem? You just need maybe to use different data set for other animals, or there is some things more to do?
Yes, so I guess you are talking about the GH nerve, the one with generalizable nerve with the human. Okay, so in case of the GH nerve, we kind of learn this generalizable nerve. So we need in the beginning lot of human data with the ground truth 2D or 3D pose, what we are trying to estimate. So in case of the humans, there is a lot of data sets available, which we can use to train our model on to get the optimize our model on this human data. But in case of the other other objects, I don't know, any articulated objects or animals, there is not enough data set to have a generalizable model in that sense, or category specific. We have to either do the category specific optimization.
Okay, I see. So it's just a problem of data set.
Yes. Yeah.
Okay. And about the dynamic scene, by the way, possible to extend your method. So you mentioned that it's a drawback right now. You are not able to use dynamics images for sequences. Is it possible for you to take into account the dynamic of your object?
So currently these methods like GH nerve or the Gaussian method, they cannot take dynamic information, because what we are doing, we are estimating novel views for the static object kind of, even though you can see it as a dynamic, but it's estimated per frame basis. So we cannot aggregate the information from all the whole scene, basically dynamic scenes, if we have a dynamic scene. So a way could be having some kind of encoder which encodes the similar image features, but in the whole temporal dimension or something like that.
Okay, I see. For sure, about your third contribution, at the end of the second one, you mean, nerves modelization with biomechanic features. For sure, right now, we're wondering why you don't use Gaussian splatting, and you use it. Okay, that's good. But in terms of comparison, you compare your method because you mentioned that you want a real-time method, and you compare sometimes with GPS Gaussian. It's a really recent method, and in terms of comparison, could you explain? Could you compare your method, your approach with GPS Gaussian?
Yes, so GPS Gaussian is also kind of similar to the techniques we use because we kind of got the inspiration from them. They are the one who first proposed this generalizable Gaussian splatting technique. What we did is like we extended their method to also adapt for human feature estimation. So in GPS Gaussian, they are only estimating the novel views in generalizable way. But we also, in our case, we extend it to learn human features or 3D pose from the generalizable Gaussian splatting. And yes, both of the GPS Gaussians also very recent method, and we didn't find any other method using the similar like generalizable Gaussians that time, at least. Yeah.
But GPS Gaussian method performs faster than your method?
Yes, yes, they perform a bit faster than us. I think they are 31 FPS or something. Yeah, I think they are.
Yes, just behind you. Okay.
Yeah. So yeah, I think they perform better because, as I said, they estimating less things like just novel views. In our case, our constraint was mostly. Let me go to the real-time performance. Okay, so in our case, I would say, yes, they were 32 FPS. In our case, the bottleneck was our 3D pose regression network because it is the only part of the network which was taking significant amount of time compared to the GPS Gaussian. That's why also when we said we tried 3 different pose regression backbones like PointNet, DGCNN, and etc. And you can see that different kind of backbones taking different amount of FPS because that's the significant part of the whole network, which is different in terms of the real-time performance. So that's why also we propose this new 3D pose regression network, which is kind of in between. Yeah.
Okay, I see. So there are a lot of people on your jury member. So maybe I can ask a last question about just a simple one, just to see to be informed. You mentioned that you have submit this work on WACCV, WICV. Do you submit during the first or the second round?
No, we submitted in the second round. Yeah. Because there was no other conference in the summertime. Basically, this was the first deadline we saw.
Okay,
Yeah.
okay. I'm wondering if you had a first answer during the first one, but no. Okay.
Oh, no.
Okay. Thank you, Arnab, for this great round, and I give the floor to your president. Merci.
Thank you.
Now I'd like to ask the second reviewer, Franck, to continue with the question.
Thank you. I could just hear that it was me next. So I wanted to start by thinking about the high level intellectual contribution here that ties everything together. It seems to me that you have a process of adding intuitions to a general system. So for example, we know that the real 3D objects you're interested in have a depth. And so you can use that depth to help you. They're not dense 3D volumes, but they have a surface with a high alpha value, and that we can use that intuition, build that intuition into our system to improve its performance. Or similarly, if we're looking at humans, then we know something about the geometry of humans, and we can use that intuition to improve the system performance. So my first question is, are there other intuitions we can build in for things like human rendering, or are there other opportunities to build in situations where we know more about the situation, more about what we're trying to render than the NERF does?
Yes, I mean, yes, obviously we can use something like, I think also a lot of the methods they uses like SMPL models or parametric models, which are like kind of providing this human geometric prior to the NERF or something. And then they use this knowledge to estimate the geometry and the 3D human from so on. But the problem with some of this like these parametric models are that they are not customizable so much. So they have a general structure and things. Maybe they are not fitted to all body shapes or the all kind of humans. So yes, we can try, like, for example, we can easily try like skeleton prior or something which is similar in all human. We all have like same amount of bones and things. This kind of prior can be used definitely, but everything has some drawbacks and some advantages, I guess.
So I wanted to ask about another potential advantage. Cédric mentioned the idea that you might do video, so XYZT for rendering, and you could imagine a system that's a NERF, but you have XYZT plus the viewing ray and maybe the inputs instead of still images of videos. Now, so my question is, because if you have a video of a human, in a still, you're using information, your knowledge of joint angles and joint positions and the relative, the structure of a human. Would there be a way of building in the intuition that we know how humans move into the 4D version? And how might you go about doing that?
Yeah, I think it's a very nice idea. And also I looked into this before, because there is the good thing about Gaussian splatting are these Gaussians representing the scene, they can be tracked throughout the video. So you can like optimize the Gaussians in the first frame, and then later on you can use the same Gaussians to just move according to the human movement and have the same Gaussians representing. So we can track all these Gaussians throughout the whole dynamic scene, and it can be very useful. And yeah, that's one of the way I think 4D Gaussians or dynamic Gaussians, they are doing this kind of way to handle the dynamic scenes. But so in our case, if we optimize the Gaussians and learn this Gaussian feature in the first frame, and then we can also have the same features and track the key points and things even in the dynamic sequence, even different frames. We just change the position of these Gaussians. Yeah, that's one of the way, but maybe other way, a lot of other methods does is that they create a canonicalized representations. So they maps this different dynamic scenes to this canonical pose, and then they remap again back to the view pose. Yeah. So
my question is also, is there a way that you could embed the fact that we know how humans move to improve the performance of the system? Because in the stills, you embedded knowledge of how humans are built.
Yeah.
Right, to improve the performance of the system. Could we embed knowledge of human movement to improve the performance of a 4D system?
Yes, I guess we humans, like all the joints have kind of like certain amount of rotation can happen and things like that, we can put this constraint on our systems to say that a human leg cannot just go up in the upside down or something like that. We can put this kind of constraint to restrict or build this knowledge inside the system. But need to understand a way to input these constraints on the, yeah.
So now the adversarial part of the question, which is you build in intuitions. Are there times, so and in many situations that helps, are there times when it hurts? So when does building in an intuition make the system worse?
Yeah, I think it's deep, like as we humans are very different from each other. So maybe it will be different, like movements can be different for different person. Like for a normal human, maybe like doing some crazy acrobatic is not normal. And if for some scenes, maybe some human doing some crazy acrobatic movements or something, and these things cannot be represented with our system in that case. So there will be some.
If you present a ballet dancer who has a bigger range of movement than the humans you've trained on, you might be in trouble, for example.
Yeah, so the edge cases mostly. Yeah.
So another version of this question. So back to the, I guess the first contribution where you're using depth.
Yeah.
I saw one of your models was I think it's the one on the screen, was a Lego.
Yeah.
Looks like Lego to me, a Lego excavator.
Yes.
And so you've got your depth estimator and it tells you how far away it is. So what happens if you've trained your system and then I show you photographs of a real excavator, which is 100 times bigger and so 100 times further away than you think?
Yeah.
What happens?
Yeah, I think for that, like this, the first method uses like normal vanilla NARP methods or MIP NARP methods. So these methods are not generalizable. So they are specific to the scene, this static scene. So for example, this, this method is just, we give the multiple input images of the scene and then optimize for that specific scene. So it cannot represent anything else. But in later on, we can do something like generalizable NARP, which uses the image features, not just the specific image. So in that case, it might work, or something like a transformer-based network to generate some more robust features for that particular object. Yeah, can be.
So a smaller version of this question is about when you add noise to the depth estimate. You're adding Gaussian noise with zero mean.
Yeah.
What happens if you add a correlator or a systematic delta to the depth? So you think everything is a bit further away than it really is. Maybe just 10% further away.
Yeah.
What does that do to your surface sampling?
Yeah, I think if we adding the same delta to all the images and all the pixels, then it doesn't change anything, because it would be just like a new 3D world coordinate will be like that. But if we are adding this delta differently with different images of the scene or in different pixels differently, then it can be a problem. And for NARF, as they do this like volume rendering in the 3D space, in that case, having this error in the depth measurement, so that means our 3D points will be like wrongly placed in the 3D coordinate system. So it can probably it will not optimize that well. Yeah.
Understood. And the final question, I guess the same sort of thing, and I'm trying to come up with a good example of how the human body assumption could be wrong. And the best I can think of is you know, I'm acting in a movie and I have 2 extra fake arms that I'm using because I'm pretending to be a 4-armed person in a movie.
Yeah.
So now we've violated the assumption that there are, you know, the right set of joints. Well, what happens then?
Yes, so I guess if we are using like a prior something like I don't know, SMPL model which only has 2 arms, and if our method only like try to find this geometry or try to fit this geometry on the scene we are seeing, in that case probably it will be able to like reconstruct the subject with 2 arms, and maybe the other 2 arms will be like very weird and don't know what to do with that. The system will be yeah,
Okay,
the system will be confused for sure. Yeah,
that's fair enough. Okay, that's the end of my questions. Thanks, Arnab.
yeah, thank you.
Thank you very much, Tom. I understand that the timing is an issue for you because it's over 11 p.m. now in Melbourne. So it's good that you had the opportunity to ask your questions.
I'm sorry, I could not hear you.
Oh, yeah.
Turn off your mic.
Oh.
No.
It's really difficult to hear you, dear colleague.
Est-ce que tu peux? Oui, mais ça fait.
On n'entend pas. On vous entend très très mal en fait.
Okay, ça va être chaud.
Alors, c'est bien.
The sound. You need to switch it.
Yeah, switch off this one.
This one is up.
Wow.
Okay, it's better.
Yeah, it's better. Yeah, that's better. Yeah, the sound. I was muting the sound.
There's one.
Non, c'est bon là.
Is it on?
Oui, oui. Il vous entend?
Okay. Can you hear us, Tom?
Yes, I can now. Thank you.
Okay, now it's better. Okay, so I was just thanking you for your questions, and we're now gonna move to the next jury member, Franck DAVOINE.
Faut qu'il reste jusqu'à la fin. Hein? Je sais.
Pas de problème.
Thank you.
Tu veux utiliser le micro?
No. Thank you, Jean. So maybe during my talk you switch off and then
No
okay,
sound.
it's better. So you hear me, the rest of the jury? Cédric, you hear me? Yes. So thank you, Arnab, for this presentation, and also I want to thank your PhD supervisors and Andrew and Tarek for inviting me today, and also for inviting me to review your manuscript. I said in one sentence in my report that I am not at all a specialist of nerves and 3D reconstruction, but it was a good opportunity for me to dive in this topic during the summer in August, and so I learned some things, some different things, and I was quite impressed by the literature in this field that is extremely vast and yes. So you addressed the problem of 3D human representation with a particular attention on the biomechanical features that are in your case the human skeleton and associated joints. And so if you first start your PhD with an introduction of your work and your objectives, and then in chapter 2 you present an overview of single view and multi-view 3D human reconstruction methods. With different representation, implicit or explicit, etc. So it was quite easy to read and a good introduction to these methods. I liked a lot the chapter 3 with a nice overview of neural radiance fields with some of the most influential methods, with some of them ensuring good photometric qualities, also others focusing on the speed, on the low complexity and speed and fast methods, others on the generalization that aim to improve cross-scene transferability. And finally, methods applied to the reconstruction of the specific object, the human. So the rest of the manuscript describes your research with the 3 chapters, your main contributions. The progressions of this work seems very obvious to me. First, with the desire to improve the accuracy of the nerve-based 3D reconstruction using the depth information, then to extend the method with the estimation of biomechanics features, biomechanical feature. Mechanics, yeah, I did not know if, it's strange. And finally, to significantly accelerate 3D reconstruction using Gaussian splatting, while still improving the rendering, the reconstruction. And so we understand that all these works, you did these works sequentially. And first you focused on the depth information to improve the quality, the accuracy, and then you made the publication, present your work in the conference. And then you extend the nerve with the biomechanics features and you write a paper. And finally, you are considering the Gaussian splatting. And this work should be, we hope so, accepted to WACV. We propose also a paper on this conference in the second round, like you, not on this topic, of course. In the introduction or in this chapter 3, you say that you say that there are more than 7,000 research papers on this topic.
Yeah.
I was very impressed by this number of papers, and you did not say where you find this number. What is your source to?
So if you just look at the main NARC paper, so it's just a rough estimate. So if you just say the citation of the NARC paper, which introduced in 2020, is now more than 8,000, I think, something like that. So it's just the papers which just cited the NARC, but there is also other papers on the related topic, so it can be higher.
It is a number that you estimated by yourself. You didn't see this anywhere, isn't it?
Yeah, even if you search in the Google Scholar or something.
Okay.
Yeah.
Okay.
It's even more.
It's even more, yeah. CVPR, etc. So in this first chapter, you give an overview of the most of some of the influential nerve research. It's quite heavy, but you have many different references. We can find new ones, of course, as you say now, and that improves the results that you present. And I was surprised to you cite the E-nerve that you will use a lot in the following chapters, but also the A-nerve, A like articulated. And so I looked at least at the abstract of this paper, and they say that they equip nerve with a skeleton to apply to time varying and articulated motion. So can you say a little more about this kind of approach and how it differs from yours?
So in case of the A-nerve, it uses the human skeleton as an input to the method. In our case, we don't have any prior, right, skeleton or something. We just have the images to begin. In their case, they have the images and the 2D skeleton or something like that as a prior. So they can use this already known information to, I think they can utilize their human models, human subject in a chemical brain using this skeleton, and then they map them to a new modes, basically. But in our case, what we are trying to achieve is like we start from no supervision about the human skeleton or structure. We estimate this structure while doing that at the same time.
Okay, I see. And yeah, so it's I guess it was difficult for you during this PhD to make a good choice and to see, because this paper was existing already, and so you could be inspired and going in this direction, adding some priors, and you didn't do. And
I think it's like during the PhD when we started, like 2020, it's the NARC paper just came out and there were some few papers at that time doing human. But most of those papers, they were using the priors, like SNPL model or skeleton or something to estimate the human. But in our objective, we wanted as from the beginning of the PhD or the topic of the PhD was to use the images and then get the everything other features from the images. So in our case, we just wanted the opposite thing. So we didn't want to have prior to begin with. We wanted to estimate those features. Yeah. So in our case, we just focus on the methods which doing similar things. And in case of the NARC, there was so many papers in the beginning for humans. And it was very difficult to find which way to go.
Yeah, sure. For a PhD student and also your directors, you have to be very, very. You need to select the good direction, and it's not always very easy to be innovative. Or so then you present your three personal contributions, and first you address in the fourth chapter of your manuscript the limitation of neural radiance fields-based methods, and in particular the MIP-NERF that was proposed in 2021 by the group of John Barron. Okay, and for this you proposed a new method that you call the MIP-NERF LGPD that leverages depth information to reduce the training time and also to improve the reconstruction. In page 74, but no need maybe to look at it, you compare MIP-NERF LGBD with other state-of-the-art NERF-based methods that are the DS-NERF, which integrates depth supervision with COLMAP, a general purpose structure from motion pipeline, and also DO-NERF that uses a simulated depth maps. Yeah. So I have, in fact, the similar questions than Cédric and Tom. This last method, the DO-NERF, is quite efficient when we look at the different metrics, but slower than your method. But I wondered how you could measure the influence of the depth information on the quality of the 3D reconstruction. But you answered already to this question, and also you made some experiments by adding some Gaussian noise on the depth. Yeah. And you answered to Cédric that if we consider a LIDAR, we could from the LIDAR reconstruct a dense depth map, always with some uncertainties, some errors, because even the LIDAR has not a constant resolution, spatial resolution on the full scene, and it could have been nice maybe to go deeper in this direction and to try not only a Gaussian noise but some imperfection in the depth map. You create synthetic imperfections, not only Gaussian noise, and see how it works. And according to you, it's difficult to feel the real robustness of this method relative when according to the accuracy of the depth estimation.
Yeah, I think it's especially like we like at that time there was very few methods was doing with the depth. I know. So there was, I think, not years. Do not was already limited by the forward-facing scenes and synthetic data. They were doing a separate network to predict this sample location by put the samples. And then there was the DSR, which was using the sparse network. So in our case, we just first we started the idea to see if it works, like just adding the depth, like the part right here, if it works to improve the photometry and geometry quality. And then from that, we developed our method with local sampling and things like that. And then when we finished, we just tried the one experiment with the noise. We didn't put so much thought at that time to have the noise, experiment with different noise and things like that. because that was not our goal at that time.
Yeah.
Our goal was just to improve the training time, because that time all the NARC methods were very taking very long time to train,
Yeah.
because they use a lot of sample points. So our goal at that time was to make it faster and improve the geometry quality. And for our purpose, it was like a choice. We did, because we knew we were not so focused on having like invest our energy on the like finding a camera, depending on the camera and make like a perfect depth. So we focus more on the we assume that we have perfect depth and things, and we just want to make it faster and have more quality, improve the depth.
Yeah.
But it's a direction we could have taken later on to have investigate this more with the noise. Yeah. But
Yeah. Because I wasn't, as I say, I'm not a specialist of this topic, but I wondered if you would use just RGBD camera. You think your method would work?
yes, so we did a paper, I think, we did our paper
With your RGBD sensor?
yeah, we tried somewhat success, but it's not part of the thesis. So we did a method called PINA.
Yeah.
Yeah, so we did the
The PINA.
yeah, with the PINA to investigate some of these things. So like is to be seated with like having RGB like stereo camera thing to estimate the depth and estimate this kind of thing. We tried some experiment, the last one. We tried some experiment on that, but after that we didn't explore this further because I was focusing more on the human side. Yeah.
Okay. I mean, Yassine, this was the first author, and he's the second author. This is a PhD student or a postdoc? Okay. Here in Sofia.
Yeah.
So in the first, so thank you for your answer. And so in the chapter 5, so you introduce your second contribution, that is JH nerf, J for generalizable, H for human. So it's an end-to-end framework for learning 3D joint locations of the human skeleton, besides the estimation of the geometry and photometry of the human subject. For that, I won't describe, because I won't describe the full architecture of your network, but it's quite. It was a little complicated for me to understand all the sub-elements of your architecture, and I think I said in this in my report that this chapter was for me in comparison with the others was a little difficult to understand, because you have so many sub-components that you interleave with some results, some evaluations. So I was a little lost, but globally I understand how it works, and so I appreciate the extensive evaluations that you made with different data sets and testing 3 different backbones for the regression networks that you are using. The PointNet, the DG, CNN, and the point transformer, and you compared all these 3 backbones and the quality of the regression. And for your evaluations, you had also to create a custom data set with ground truth, 3D pose, 2D key points, and dance pose. So this work was difficult to do, and how many weeks or days you spent on the creation of these data sets? You made it in Sofia or in Brown University, or where?
Well, the generation of the data set was quick, because we started with there is a data set called human 2.0. They have like 500 something scans of human images, and also they provide like repeated SNPL models and things like that with so we just use this data set to simulate like new camera angles. We place the scan in a blender or whatever, and then we just generate new images from different angles, things like that. So it was not so time consuming is because we just wrote the code and then we run it for like with different instance. It was like 1 day.
1 2 days, okay. And this data set is made available to the community?
Yeah, we plan to do it because we will just made available the scripts with generated data sets because we don't have access. We cannot give you access to the models because the model belongs to the team 2.0, but we can make the scripts generate these data sets.
And also for this GH-nerve, you made an interface to interact with the human body. And this software also is available on the web, or it's not? You will make it available for to the community or not?
This paper, like we already published it, I didn't come much back to put the code in GitHub so far, but I plan to flip at some point. But this software, it's a very popular framework. A lot of the NARP methods uses, like Instant NP and everyone else.
Right.
So you can find a similar framework in other NARP methods.
Okay. Okay. So I will maybe skip one question, but keep another one. So still, last question. Sorry, no, I go too fast. Okay, so in chapter in the last chapter, chapter 6, this one is quite easier to read with Gaussian splatting, and you present quite impressive results in terms of real-time performances, 25 images per second. It's quite good. So you describe an original method named Human Feature Gaussian, HF Gaussian, utilizing Gaussian splatting for predicting in real time biomechanics features from pairs of 2D images. I wondered, you select pairs of images. You have an image and you take the previous one and the second and the next one. No.
Not exactly like that. So the data set we use for this experiment.
Yeah.
So data sets are generated such a way that there is like a person standing in the middle, and then you have 8 different cameras around it.
Yeah.
Each one is 45 degrees between each of them. 45 degrees. So when we generate the novel view, we decided we can generate a novel view from here. We take the neighboring cameras of that novel views from these 8 views we have as the input, and then from that we learn the method. So in the test time, what you do is like you need a similar kind of data set. So this is a test set. So in this case, they also have this human doing different movements in the middle, and you have 8 cameras. So we have a training model. We just want to generate another view. We just have the camera coordinate or the 3D extensive images of the camera, and then we just check which are the closest view of the data set, and then it's generalizable, so we can directly estimate the novelty of them.
And is there any interest to take more than two images?
For us, the 2 images were fine because we need 2 images because the depth is very important. Uses like this video vision kind of assumption to generate the depth. So that's why we need to use, that's the minimum we can. So we can have more.
You could have more and improve maybe your results. You did not try to extend.
For example, the GH-nerve, the previous one, they use a small views. So they combine from all the views. It can be 4, 8, or 2. But this one, we just leave the 2 because we just want to have real-time performance and use as less as possible.
Okay, sure, of course.
And also it gives us more flexibility.
Okay. So your architecture that you proposed is, as said Cédric, it was inspired by the GPS Gaussian method that was proposed in 2023, and with different elements also, and you are using also a unit within your architecture. small, some encoder, some MLP, etc. It's similar to, clearly inspired by the GPS Gaussian method. And it's yes, it's a full framework that gives impressive results. I say again, I was happy to see some animation in your presentation, because on the paper I looked at on your web page, but you don't have such nice. I think I recommend, if you want to make your work visible and more attractive, you can put some video animation of your results. Ah, okay. Yeah, sure. Yeah. So again, I appreciate the extensive evaluation you made with different data sets. Again, testing 3 different backbones for the regression network. You compare, so I will skip this one. We know that the optimization process of 3D Gaussian splatting prioritize updating the appearance of 3D Gaussians rather than directly moving them to the desired 3D locations. And to enhance the geometric optimization, do you know some work or some solution you could imagine to separately optimize the geometry, that is I mean the 3D point positions, and the Gaussian attributes, I mean the texture? Do you think you could separate these two in your optimization in order to improve your results? And do you have seen some works on it?
Yeah, in our case, we also kind of do it. And if you can see the depth estimator module, we first train the top one, like this one.
Yeah.
In the depth estimator module, we estimate the depth of this source fields, right?
Yeah.
So when we start this optimizer, first we train this module to make it as good as possible to estimate the depth corresponding to the source field. So in that way, we are kind of supervising the depth training of this in the beginning.
Okay, yeah.
Yeah, so we are using the depth supervision somewhere because we are trying to predict the depth of this source.
Okay, I see, thank you.
And another thing to mention, as you said, the location of this Gaussian are generated using this depth method. So it's very important to have a good depth estimate in the beginning. That's why we train the depth module separately to the beginning, so that when we test the Gaussian based on this depth, they are already pretty good location in 3D space. And then from that, we can optimize the Gaussian.
Okay, thank you.
Yeah.
It's clear. And I will finish with your perspectives and your conclusion. The perspectives, you list a lot of 4 main ideas, and you say we could, for example, consider the dynamics. I would have liked to see some, not only some what we could do, but how we could do, and on some points. For example, I will focus on one point. So, because I looked at the literature also, and there are some papers that are considering just for maybe more for the generation, they are using generative adversarial networks, and also other methods are considering large language models to generate some priors, because in your case you refer to some works that are using the SMPL body model as a prior. But now I have seen many, a huge class of, quite a lot of number of papers considering text, large language model and combining text and image to either to generate this kind of 3D model and also to animate the 3D model of the body, and using clip and using all these tools in this new domain. What do you think about this? And do you just to take some, if you would start your PhD today, you know you have all your experience and your research, you see such new papers, with large language models, and it's maybe not the good way to follow, but what do you think, and why did you I didn't see any reference in your PhD on GANs or on large language models. Why?
Yes, because we, since the beginning, we focused on NERF, and it was already very lot of like research on the
Yeah,
NERF, and
yeah.
it was very already hard to find a niche inside the NERF and having contribution.
Yeah.
And if we include the GANs and things, they came a bit later. The NERF, like I think it's used last year, fusion and models like this, which use a SNARF or
Infusion, yeah.
triplanes to
Yeah.
construction. But since last year I just focused on my things. But yes, if I start now, it's probably gonna be a good area to look into because it's generative, so we don't need maybe even supervision so much. It can be a new area of interest. But yeah, I didn't put so much focus on that. But yeah, for this topic, because we in our PhD we had a particular goal.
Yeah. Okay, but at least I see you know this kind of approaches. Okay. So I will finish with my questions here, and I thank you again for letting me reviewing your manuscript. And as I said, it was quite interesting for me and for now, but maybe for perspectives in my lab. Thank you.
Can you use your mic?
Yes.
Okay, thank you very much, Franck. And I would like to call Professor Srinath to follow up with the questions, if you can hear me.
Yes, I can. Thank you. Can you all hear me fine?
Yes, we do.
Okay, perfect. So first of all, Arnab, thanks for the really nice presentation. I think you have a good body of work that you've done over the last several years. We also really enjoyed having you here at Brown. Thanks for your visit and spending a few months here collaborating with us. So I have a bunch of questions. I'm kind of going to separate them into lower level questions and perhaps higher level questions. And because higher level questions probably don't have very simple answers, I'm going to start with the lower level questions first. So going to your first contribution, which is the depth-based NERF method that you proposed, I had I guess, a practical question here. How do you foresee getting depth for scenes? I mean, for indoor scenes, I can imagine that you can use RGBD cameras. Oftentimes, RGBD cameras don't work so well, for example, in outdoor settings or when there's like bright sunlight that affects the infrared perception of these cameras. So what are your thoughts on that? And do you see any other way of obtaining depth other than depth cameras?
Yeah, so recently I saw some methods which can estimate depths from the images. Like I think there is a model from Meta. I think they were doing, they estimate depths of anything. It's depth anything or something like that, the name of the model, where they can estimate the depth for any images. This kind of model can be used to have a depth estimate to begin with. Then we can optimize during the training process to make the depth more accurate or something like that. Yeah.
Okay, all right.
Yeah.
Sorry, please continue. It seems like you had something more to say.
No, you can hear me, right?
Yes, I can hear you.
Okay.
Yeah.
Okay.
All right, cool. Sounds good. The other question that I had was, I guess it's somewhat related to your second and the third contribution, where you kind of combine some of these, neural radiance fields, Gaussian splatting with pose estimation. I think we've had conversations about this before, right? One thing that I really find surprising is that this line of exploration, investigation, doesn't seem to be as popular in the sense that people who work on radiance fields seem to have this relentless quest towards improving quality, perhaps reducing the number of cameras, but we rarely see analysis of these radiance fields in the sense that once you have the radiance field, what do you do with it, right? And I kind of see your work as kind of taking a step towards that, right? Do you have any insight on why the community isn't kind of looking at some of these analysis problems as much?
I mean, I would guess that the most of the paper currently we see is like they are trying to improve on the previous state of the art in terms of either photometric quality or geometric quality, just to get paper accepted in some conferences. So I would guess they are just trying to find new way to do the same thing, but improving, but not focusing so much on what we can do with these things. Maybe it will be changed in few years when this field will be mature a bit more and this kind of thing, and then people will focus more on the applications or what we can do with these things. Yeah.
I mean, apart from the the publishing constraints here, do you think there are technical reasons for why that has not been the case? For example, perhaps the quality of these reconstructions is not yet at a level where it allows these kinds of analysis applications. What do you think about some of those technical challenges? And do you have like more technical challenges that you think are preventing that?
Yeah, so first thing, like if we consider the humans, there is not enough ground truth data for like human features like 3D pose or something which or enough variety of the human data to have a generalizable model in that sense with these ground truths and everything. So maybe that's a challenging situation for everyone to do like methods, like proposed methods, which using this kind of priors or something to estimate more insight in the nerve with humans or something like that. Yeah, having more data on human would be a good start.
Okay. You've also worked with both neural radiance fields and 3D Gaussian splatting. How would you compare and contrast these two? I mean, the end result of both of these approaches, loosely speaking, is a radiance field, right? And how do you compare and contrast these methods in terms of the advantages it offers towards your ultimate goal, and disadvantages of either one of these methods?
Yeah, so Gaussian splatting and NARP both has like some of the drawbacks and some of the benefits. So in case of the Gaussian splatting, as we've seen that they are very good at for estimating very quickly and for the rendering speed because of the explicit representation. But in case of the NARF, we have a continuous scene representations, which can be useful in some applications. And some other application, we just want to have a rendering as quick as possible, like video games or something, where Gaussian splatting can be more beneficial in that sense. Yeah, but I guess it's more depend on what we want to achieve or what we want to do with our method. Yeah.
Okay. Yeah, let me move on to some more high-level questions connected to the contributions in your dissertation. The first thing that I want to kind of ask is, the term biomechanics features prominently in your dissertation. And if you look at the definition of what biomechanics is, obviously it involves skeletal motion, but it also involves the connection to the musculoskeletal system, the forces that are applied to the musculoskeletal system, and how this impacts both body motion, but also how this impacts the environment and so on, right? So I'm trying to understand and get your thoughts on this, right? Like, how do you see the connection to biomechanics as a whole versus the kinematics, which is what you seem to have explored so far in your work, right? So could you try to relate these two things and why you think what you've done is perhaps more than just the kinematics?
Yeah, I think we had a discussion about this also sometimes ago. It's so basically our goal was to have this biomechanics properties like forces acting on some joints and things like that. But for the time constant, we didn't have so much time to think about these things. But yeah, the current research can be like a starting point for this thing. So if we can estimate this like properties as simple as like 2D or 3D key points, then from that maybe we can estimate the joint angles or the forces acting on the body by fitting this kind of kinematic models they have in some of this biomechanics research. And then from that, maybe we can estimate some of this properties or some of this this forces or something on the joints and stuff like that. So it can be a starting point after this to have more focus on the biomechanics part and how we can use this information.
And do you think radiance fields as a presentation is well suited for this kind of analysis?
I would say maybe Gaussian splattings are more useful because it's easy to track them throughout the like in 4D or something, because each of the joint can be represented with a single Gaussian, and then we can just track those Gaussians throughout the scene and easily calculate the movements and stuff like that. So maybe Gaussian splatting is much suited for these things. Yeah.
Okay. Sorry, I realized that I had forgotten one of the lower level questions. So let me maybe ask that first before my other question. So you talked about I believe this was for GH nerve, you talked about the real-time performance, right? A quick clarification there. Is this on comparable hardware, or is it on like, different machines, or do you run it all on the same hardware and then compare those numbers?
Yeah, so for our test, we ran all of them in the same hardware, like 3090, a single 3090.
Okay, and it's all under the same conditions.
Yes,
that
yes,
you
yes.
compare it. Okay.
Yeah, we use their official code for all the experiments. Yeah.
Okay. Yeah, I guess final kind of high level question that I have here is, you talked about future work, and you mentioned multiple people, being able to analyze multiple people, faster optimization, etc. Would you like to, for each of the future work items that you presented, would you like to talk about, first of all, how your work can be extended to it, and second, what do you think are the challenges and opportunities in realizing each of these future work topics?
Yeah, for example, multiple human would be a good start to begin with, because most of the cases, the general scenes involve multiple humans or interactions, which generally we are interested in. So I guess to extend our method to this multiple human, we can start with first maybe doing a bounding box around each of the persons in 3D, and then optimize the separate Gaussians for each of them. And then from that, we can combine them together. Something like that would be a good start, but maybe we need to do experiment to see if it works or not. Yeah. And for other things, for generalizability, I think having data about other animals or objects can be good start to generalizable, more category specific, or more generalize all the categories at the same time. And then for efficiency, for training time, I think there is already some methods. They are improving this training times for Gaussian splatting with different techniques, so we can look at some of them. And for dynamic scenes also, there are some recent work with Gaussian splatting using dynamic scenes and temporal consistency and things like that. We can look into that. Yeah.
Okay. That kind of also, sorry, this is probably my last question, but what you just said kind of reminded me of connections to another topic, which is not directly related to your topic, but nonetheless, there's a lot of attention being spent on that in the computer vision and broader machine learning community, is being able to generate images and videos using these generative models, diffusion models in particular. Do you see any of these models as potentially being useful in addressing some of these future work directions that you're talking about?
Yeah, I guess it depends on what kind of application we want to do, because these generative models, they are not generally very good in providing intricate details or very complicated structure or very detailed structure of the model. So currently they are not useful for applications such as medical domain or something where we need more custom and accurate geometry and photometry of the person, something like that. But maybe for other things, like if we are generating some characters or something, maybe there is more useful to have generative models.
Okay, cool. All right, I think I'll stop there. Thank you.
Thanks.
Thank you very much. Yeah, sorry. Thank you very much. I'll be very fast with actually quick time. I enjoyed your presentation. That was very well structured and well illustrated. I just have one simple high-level question regarding this dynamic scenes.
Yep.
Future work. It has been already discussed with Tom, and I'd like just to know what kind of challenge you envision, you see for tackling dynamic scenes or outdoor scenes with very fast motion. What kind of problem and challenge do you see, and do you have some ideas how to tackle them?
Yes, so I would say for fast motion scene, one of the challenges would be the consistency between two frames, like moving some arms or something, they have to be in consistent motion from one frame to another frame. Sometimes for currently, we are doing the dynamic scenes like a per frame basis. So in this case, like you see that there is some glitches or something like that, but maybe if we have the whole thing predicted at the same time and take into account the movements of these parts, then it would be much more homogeneously moves through the time. Yeah, that kind of thing. And then also like occlusion, like in dynamic scenes, generally between two frames, sometimes we miss some of the part of the arms or something or occluded in some movements. So having this, maybe it would be a challenging for dynamic scenes to figure out this problem. Having a 3D reconstructions throughout the dynamics, it can be challenging in that sense. Yeah.
Oh, okay, I'll stop here with my questions, and maybe I give the mic to Tarek, who is the co-director of your work.
Yeah, I don't know if you can hear me. I'm the official director of the thesis. I did nothing. I'm not really the supervisor. This is why I asked Arnab to change the first slide. I'm the director of the thesis, and Antu is the supervisor.
Oh, okay.
There's no director and co-director. I'm the director, he's supervisor. I don't have any question. I risky all this path, and I would like to thank the member of the jury, especially Tom DeMond. He spent a lot of time with us after the problem that we had a year ago with Andrew from DAVOINE as a referee, and Cédric also from the reports, and Jean-Martinet because he did some work with you recently, and Srinath because he did also some work with you in the US.
Yeah.
And I guess I stop here because we don't have a lot of time. And I'm happy to see you over here and maybe have some more to say about your thesis.
Thank you. Okay, now our final jury member and for COMPORT, and may I ask please that you shut off your mic
okay,
and also the sound.
okay.
So can you guys hear me? Yes, okay. Yeah, so I guess I'll just try to be short as well because Tom, it's gone probably past midnight by now. But yeah, I just wanted to thank the rapporteur for their solid investigation into the manuscript, and thank our international jury members for getting up early and staying up late, and also for participating and helping out for this last year of the PhD where I haven't been present, and also to thank Jean and Tarek for taking up the relay for this last year. It's very impressive, Arnab, what you've been able to do in this last year. You've been able to pull it all together, and it's great to see that that you've able to stick to the initial objective all the way through. So you've got a bit of each of the elements that we were really looking for in the beginning, which is using some state-of-the-art representations to capture human motion or human scenes, and to take that through into some sort of real-time analysis. So you've managed to hold on to those key concepts. Maybe just a short question on the last bit, which is the future work and limitations. So I think one underlying theme that's interesting for me in this thesis is the underlying representation. So classically for 3D reconstruction and scene movement, we've had point clouds, and we've had surface models, and we've had volumetric models. And here, during this thesis, you've really investigated this neural MLP style representation of the scene. And then you've taken that a bit further with this more efficient Gaussian splatting. So I'm just wondering, in terms of underlying representations of the world for rigid and non-rigid representations, efficiency, what are your thoughts on the future representation? What will be the key way of representing these scenes?
Yeah, I mean, there is two kinds of representation, as you said. We discussed in the thesis is the implicit, like nerves and things like that, and then explicit, like Gaussian splatting. In case of the Gaussian splatting, it kind of similar to like point cloud representation in some way, because we are still storing all the Gaussians with their parameters to represent the scene. So it still takes a lot of storage, but it's faster to render. But on the other hand, we have the neural gradients field, which takes very less storage, but it's slow to train because it's continuous representation. So yeah, so I think it's depends really on what we want to do after with the representation. So maybe if we are looking in the representing some scenes, but we don't have much storage, maybe implicit representation can be better in that case because they are generally very small. But in case of the Gaussians, if you want to have some fast systems, don't care about so much about the storage, then maybe Gaussian splatting is the way to go. Because in Gaussian splatting uses millions of Gaussians to represent the scene. So which is not ideal for many applications. So yeah, it's really depends. For the moment, both are still in the progress, so maybe we get something in between, like instant entity or something, which uses some voxel breed or something.
And just like a last question in terms of limitation, like, did you find any kind of key scientific hurdle in achieving these goals that you don't really see a solution to, that is really something that needs to be solved by the community?
Yeah, still for this kind of method, we still rely heavily on dataset. So having a good dataset or a standardized dataset for the community could be a good starting point with all the our ground truths. So having a dataset with large amount of data with the ground truth, and if we can use all the method, use that dataset, it would be a good starting point to compare it with everything. And also to improve on this. Yeah.
Okay. Well, thanks, Arnab.
Okay, thank you very much. So I think we all had the opportunity to speak. So now we're gonna go to the next step where the jury will deliberate. So I would like to First of all, to ask if there is any question in the room. And I guess not. So I would like please to ask you all to leave, and we're gonna deliberate now. Please, jury members, stay with us. Arnab, can you please switch off the broadcast?
Yes.
Thank you.